Okay, so we have seen that to compute distances in the graph, we can go and proceed in layers. To proceed in layers and deal with this node first, then this node, these nodes second, then these nodes, we needed to use a data structure that we call the queue. Again, a queue is think about it as a list that has two endpoints. One is called the head, one is called the tail. That when we put things, or the operation we call is in queue. When we want to put an element x on the queue, suppose this queue is called q, we have an operation that's called in queue, where we add an element x to the queue. It is implicit that x is going to be at the tail of the queue. Okay? And when we want to process a node, when I say it is time now to compute the distances to all the neighbors of 1, then we have to get one out of the queue. And for that, we use an operation called dq. And there we just specify the queue, because you cannot access the queue in any way you want. When you say, I want an element from the queue, you will always get the element that's at the head of the queue. Okay? So you equipped with this data structure of queue, and with these two operations, the only operations we need on the queue, now we can actually implement this algorithm, or think about writing this algorithm formally in a clean way. And the way the algorithm will proceed is that first, we will put only node 0 in the queue, right? Because it is the original node or the source node from which we are computing distances. We will put node 0 in the queue. Then, after that, we will say, okay, let's look at all the neighbors of node 0 whose distances haven't been computed yet. For each one of them, we will update its distance by saying that d1 is d0 plus 1. We will compute the distance to this and compute distance to this. And for each one of them, when we compute its distance, we immediately put it on the queue. So we say d1 equals 1, put 1 on the queue. d3 equal 1, put 3 on the queue. d4 equal 1, put node 4 on the queue. Once we are done with this, 0 is already removed from the queue because we have dealt with it. Now the queue is going to have 3 elements on it, 1, 3, and 4. Then we say, okay, let's process things that are on the queue. We take node 1 from the queue, process it. Now 1 is removed from the queue. We deal with all its neighbors. When we are dealing with them, since 0 and 3 have been dealt with, neighbor 2 hasn't been dealt with, we add 2 to the queue. So now the queue has only 3, then 4, then 2, and so on. Okay? So this is a clean way of keeping track of which nodes have been processed, distances to them have been computed, which nodes we still have to process. Okay? So it's very important to emphasize the significance of data structures. In this case, we needed this data structure of a queue. I could have used a set to put these nodes in it. However, a set is an unordered collection of items. It's not gonna we are not going to be able to keep track in a set of which node was processed first, which node was processed second, and so on. Okay? So the choice of a data structure is crucial for the algorithm. And sometimes multiple data structures can work. However, the choice of the data structure, even among ones that work, might affect the running time of the algorithm. So it's very important to keep in mind that consideration, that the data structures play a crucial role in the running time, or dictate the running time of the algorithm. So here in this algorithm in BFS, we have seen one of the first data structures in this course, which is called a queue, and it is crucial for this algorithm. So every time you want to maintain a list of items, in the same way you can think of a queue in a cafeteria or at a bank or in a hospital, for example, this is how you would, this is the type of data structures that you would use. Okay? So now that we are equipped with this data structure of queues, now we know how to deal with the graph in layers. We have just to pay attention to a few more details. The first of which actually has already occurred here, is that when I'm computing I computed the distance to node 1, and d1 equals 1, and then next time I say, okay, let me now look at all the neighbors of 1. And suppose now I'm looking at this neighbor 3. If I say the distance to 3 is the distance from 0 to 1 plus 1, I'm going to get a distance of 2. However, we have already visited node 3 through a much shorter path of distance 1. So it is very important when we are dealing with this algorithm that when we check the neighbors of a node, before we update its distance, or before we say here's the distance to this node, the first thing we need to check is if the distance has been computed. Okay? If the distance has been computed. So how would we do this in an algorithm? One of the common ways to handle these kind of cases is to see, has the distance been computed? Is before we do anything in the algorithm, the first step we do, we initialize the distances to all nodes. We initialize every dj, for every j in V, for every node, we initialize dj to infinity. Okay? So this will be the first step, saying that the distance from node I to every node is infinity, okay, including to I itself. Then after that, when we come to handle a neighbor, the first thing we need to check is dj still infinity. So in this case, when I am computing the distance to node 3 coming from 1, the first question I will ask, is d3 infinity? If d3 is infinity, it means that we have not visited it through any other path, which means it is time to update its distance from infinity to some finite number. However, in this case, when I come from node 1 to node 3, I say, what is d3? Is it infinity? The answer is no, d3 equal 1. Therefore, I don't have to touch it. I don't have to modify it. Okay? So this is the first issue here, that when we come to a node, there might be multiple paths to that node from the original node. And we have to make sure that the first path that reaches that node is the path that decides the distance to it, and all other paths should not touch it anymore. This is number one. Number two, which is a boundary case that we have to be careful about, and is going to be already taken care of here by this initialization, is that we need to keep in mind that let me say that it is very natural for all of us to assume that the graph is connected. But you have to be careful about boundary cases with algorithms. It might be that the user has a graph that also has nodes 6 and 7 that are connected to each other, but they are not connected to node 0. So now what is the distance from 0 to 6 or from 0 to 7? It's infinity. So we have to make sure that the algorithm says that d6 equals infinity and d7 equal infinity. We want this as part of the output, okay? Because notice that the way the algorithm is proceeding is never going to reach 6 and 7, because there's no path. These are not the neighbors of any of the nodes here, okay? Fortunately, this is already taken care of, because as I said, the first thing the algorithm is going to do is that for all nodes in the graph, it's going to initialize the distance to infinity. So after the algorithm is done, at this point, after it dealt with nodes 2 and 5, the queue is going to be empty. There's nothing more for the algorithm to do. It's going to return the d values. And when it returns the d values, it's going to return 0, 1, 1, 1, 2, 2, infinity, infinity, which is the correct behavior that we would want from this algorithm. So with the use of the queue data structure, with the knowledge that there might be multiple paths from original node to any given node, and we have to keep track of that, with the knowledge that there might be nodes that are not reachable from node 0, and we have to return infinity, now we are at a point where we can write the full description of the BFS algorithm, which again proceeds in layers. In every layer, it assigns distances to nodes at that layer and pushes all of them on the queue and proceeds until the queue is empty.